Okay, so good morning, everyone. So we'll just continue from where we left yesterday. So yesterday we discussed about um, maximum likelihood method, and particularly in one variable, one parameter case, and then we discussed about how to obtain the uncertainties of the errors on the estimate uh, by 4 different methods. Okay. Now let's move to a case where you can have, say, perform the maximum likelihood fit with 2 parameters. Now this is an example where you have kind of a data set obtained from using say 2 parameters, okay, alpha and beta, with a PDF which is basically a quadratic function. So this kind of PDF describes the angular distribution of some scattering event where the scattering angle x can be characterized. I mean, the x which in angle theta will be basically characterized as x equal to cos theta. So if the measurement is restricted within some certain range, you can do variable transformation to get the PDF in that range x into x max. Now this data set, which is example taken from that book, it's generated using this parameter value alpha equal to 0.5 and beta equal to 0.5, and 2000 events have been generated, and then you try to perform the maximum likelihood fit, assuming that you don't know what is the value of the alpha and beta, but you know what is the PDF. Okay. And this the fit, you can see that when you do the fit, this matches pretty close to what has been generated, and the fit result is around the same value 0.5, but with, say, in one case it's like about 10% error for alpha, and for the beta it's about, say, like 20% error. Okay, now we can see what is the errors. This errors that is quoted there, it's basically estimated using this RCF method, where you can compute the double derivative, okay, of the likelihood function with respect to the parameters, and the values for the as in the previous case, you can see that the obtained errors here 0.52 and 0.1, and the estimated covariance is around 0.0026. Okay, or the corresponding correlation coefficient, which is given here. Now you can understand the same thing, or perform the measurement, perform the estimation of these errors by using the Monte Carlo study. Okay, as we discussed earlier, one of the method to estimate the uncertainty is using Monte Carlo study. So here you can, once you get the results of the fit, you can perform or generate Monte Carlo data sets. Okay, for each experiment, you generate the same number of events, say 2000 events, and in this case generated 500 such so the experiments, each having 2000 events, and then for each of this data set you perform the maximum likelihood fit, and you obtain the parameter values. So then you can get the sample mean. Once you get this parameter values, you can look at the, once you have the parameters from each of these measurements, then you look at the distributions, and you can get the sample mean, which is the average. And you can see that the sample mean from this is, so look at this, the results of this. So once you get measurements from these 500 experiments, so you can look at the distribution. This is showing the distribution of these estimates alpha and beta in 2 dimension, and then their projections or marginal PDFs in 1 dimension. So you can see that the marginal PDFs are almost like a Gaussian distributed. Okay, so from there you can get the corresponding mean and the width of this or the sigma of these distributions will give you the uncertainty on alpha and beta estimates. Okay, so that's what it's quoted here. So the average of these distributions is the value of the estimate, and the width of these distributions would give you the uncertainty on this, which is very similar to what you get using the RCF method. And similarly, also you can calculate the covariance from the distribution, and this is also matching with what you calculate from the using the RCF method. Okay, and now you can also do this graphical method and vary in the values of the alpha and beta, so that the log likelihood varies, it decreases by half, okay, from its maximum value, and that shows the contour in this alpha beta plane, which this contour represents where the log likelihood value is half it's the maximum value of the log likelihood minus half, okay, and then you can see that the tangent. So this is you can see that this is like an ellipse, okay, and the tangent to this ellipse gives you the one standard deviation, or the uncertainty for individual the parameters alpha and beta. Okay, so from the horizontal one, the tangent will be the error on alpha, and the vertical side the tangent will be gives the error on the beta. And you can also see that in this case, the estimated value lies within the 1 sigma contour of the true value. And you will see this kind of plots many times in your own experiment, when you determine some parameters, measurement some parameters in the experiments. Okay.
Sir, can you go back to the previous slide?
Yeah.
I had confusion. So, sir, the parameters alpha and beta, are plotted in two dimension, and this ellipse is the result of what? We have the fit value for alpha and beta, which is shown here, the ML fit result, and
Yes.
the true value one should expect is shown in this black marker circle. Okay. So I just wanted to confirm what is this ellipse? This is a fit or something else?
Yeah, the ellipse is basically the points, okay, where you have the maximum likelihood, you maximize the likelihood, right?
Okay. Okay.
You maximize the likelihood, you get the best fit value, right? Now you can change the value of the parameter alpha and beta,
Mm-hmm.
and then find the position where the log likelihood is the
Maximum.
maximum value of the log likelihood minus half. The maximum the log likelihood decreases from the maximum likelihood by half.
Mm-hmm.
Okay, so if you find all these points that corresponds to the values of the alpha beta, where the log likelihood differs from the maximum value of the log likelihood by half.
Okay. Okay. So I understand. So basically, it's a continuous locus of point,
Exactly.
and from the which the best is the triangle one. Okay. Okay.
Yeah, the best fit value is the triangle one, which maximizes the likelihood. Now you can find the points where the log likelihood differs from the maximum value of the log likelihood by half.
Okay. Okay.
Okay, so that point corresponds to 1 sigma contour.
Okay. Okay.
Okay, and the tangents of this ellipse gives you the 1 sigma for the corresponding parameters, individual parameters.
Okay. Okay.
So you can always have this 1 sigma contour, 2 sigma contour, and so on. Okay.
Yes. Yes.
So this is coming from, so here we discussed in this slide, we discussed for one parameter values where the log likelihood decreases from the maximum value of the log likelihood by half. But when we have more than one parameter, you will have the contours.
Yes, correct. Correct.
Okay.
Yeah.
Okay. So yeah. Now you can also one can do get an analytic expression as well in this kind of cases. I mean, in particularly this case, if you take large sample limit, that is the number of events in the sample is very large. So in that case, one can and do the calculation and approximate this, and you can find that the values of that contour where the log likelihood uh, you can write the log likelihood equal to the maximum value of the log likelihood minus this expression. Okay, and to get where this is to get the contour of the one sigma contour, then you have to basically equate that this second part of this equation is to be half. Okay, or since you have 1 by 2 factor, so if you remove that makes basically this expression here to be 1. So if you do that, the points that you get for alpha and beta will give you that contour. Okay, and one can also find the angle of this ellipse. Okay, and with respect to the alpha axis, which is given this expression. Okay, this is kind of what I understand. It's kind of a special case, okay, where you can do also analytic calculations. Okay, now we discussed cases.
Sorry,
where,
sir. Can you go to previous slide? So
yeah,
you this angle is what? These are phasors. I mean, I could not understand
the
because
angle is the angle here with respect. This is the ellipse, right? This is not this tilted. So
yes,
you
yes,
have a correlation between alpha and beta, right?
correct,
So
correct, sir.
that angle with respect to the alpha axis.
Oh, okay, okay.
Okay. Now, so far, whatever we discussed, we assume that the number of observations n is kind of fixed. Okay, but it is possible that you can have the number of observation itself is a Poisson random variable. Okay, for example, in some cases like where you are doing the fit, but when you do the fit, you assume that uh, the number of events that you obtain, that is the cross sections of or the cross section times luminosity that you expect, the number of events that you obtain from the data, that is some kind of a Poisson variable that you want to also estimate that along with the parameter itself from the fit. Okay, that this number is not fixed. So in that case, you can treat that number again is a random variable with a mean value nu. Okay, or expected value nu. Okay, and then you in addition to the joint PDF for the parameter, okay, you also multiply a additional probability, Poisson probability to that, which defines the Poisson probability to find the n, given the actual value is nu. Okay, so that gives you a Poisson probability this part. So here we are treating the total number of events that is observed in an experiment. It's not fixed, but it is actually drawn from a Poisson distribution with an actual value to be nu. For example, you got some number of events, okay, from some experiment, but you expect that uh, the true number of events, given that you have a cross section times luminosity, and this is some number, some expected number, which is not exactly known, and you want to find what is that exact number. Okay, so in that case, then you can see that the total the likelihood will be product of these two probabilities. Okay, and then will look like this, where in this kind of cases it is called the extended likelihood function. Okay, so you can have two possibilities in this case, or two possible situations where the nu itself, okay, the total number of events itself is a function of theta or function of the parameters, or you can have the nu is an independent parameter, is an independent of theta. Okay. So in that case, so let's take the first case. So when nu is function of theta, then you can expand this, log likelihood function. So you'll get log of L theta would be n log nu, which is function of theta, minus nu, which is again function of theta, plus log of the standard one that we had before, plus some constant term which you can ignore, because when you maximize this becomes 0. So then you can rearrange this, and you write this log of L would be minus nu plus sum over product of the log of product of nu as well as the F. Okay. So here, that means including this Poisson term, the resulting estimated theta also exploits the information from the number of events that is observed. Okay. So the theta not only exploits the distribution of the observable, but also the total number of events that is observed. Okay. And this will also lead to smaller variances in theta. Okay. On the other hand, if nu does not depend on theta, so you can just simply, that means simply the estimate of the nu would be basically the number of events. Okay. And theta e will be basically the same as the usual ML case. Then you can separately treat it. However, it is still helpful to use the extended maximum likelihood in some cases where, say, the PDF is simply the superposition of several components. Like if you can write f of x theta is basically product of sum of the product of the parameter theta I times f of fi of x. Okay, where the f of I x is well known, and theta i's are all independent, and sum of this theta I would be 1, constant to 1. Okay, in such cases, the log likelihood would become like, say, this term mu plus sum of the log of this product terms. Okay. Now you can redefine.
Sir, how are theta is not independent? Can you give an example?
Theta is not all independent, means one can, the parameters are not completely independent. One can write one parameter as sum of the other. So for example, when you constrain it, so you can write, say, theta 1 is 1 minus sum of theta rest of the theta, right?
Sir, are these parameters or different parameters or different values of the same parameter?
No, different parameters.
Okay.
But you can have, not they are not completely independent.
Okay, sir.
Okay. So in such cases, now you can redefine, say, this mu theta I times nu as mu, and mu are not subject to this constant, that sum over mu equal to 1. Okay. And then the log likelihood function would look like this. Okay, this sum over mu I, sum over mu j times log of sum over mu j and f of x I j. Okay. So here, then, so here this sum over mu j, basically, if you get the estimates for mu, okay, the means of the mu I, then sum of this will become, say the n, the total number of events. Okay, and then here this estimators mu I, this can directly give the estimated mean number of different type of events that you expect, which is equivalent to say mu I, which is times theta I times mu. So mu hat is total number of events, but you can imagine like say mu I is maybe contributions from different number of events. Okay. So okay, let me come to an example. Maybe this will be easy to understand. Okay, this become a little bit of abstract. Now let's consider this example where you have say two types of events. Okay, you have signal and background, and the total data consists of both signal and background. Okay, that you get as an observed data set. Now suppose we know that the PDFs of the signal type, which is Gaussian, and the PDF of the background type, which is say exponential. So you have an exponential falling in spectrum. Then on top of that, you have a Gaussian. Okay, and the number of signal events is ns, which is Poisson distributed with mu. I mean ns is and number of background events is nb, which I mean, that is what we want to estimate, what is ns and nb, where again, this is Poisson distributed with a mean mu. Okay. Now you can rewrite this PDF as here, as we said, right? So you can factorize the PDF as theta times f of x, right? Theta j times f of j. So here you write this PDF, it's sum of the PDF of the background plus signal, and then normalized to signal plus background, normalized to n. So this is mu s over mu s plus mu b times f of x, f of s times x, and then similarly for the background signal. And the total number of observed events n is ns and nb, and we want to estimate what is actually the true value of the signal in the background, which is mu s and mu b. Now this kind of fits you may have done in RuFit already. Okay, so then what you'll do is you'll simply feed this function to the total number of events. Okay, so this is a data sample where it is generated with mu s equal to 6 and mu b equal to 60, and then you perform the extended maximum likelihood fit with both mu s and mu b as treated as the parameters. Okay. Then when you fit it, you will get given this as the initial number to generate, and you give the fit with assuming that you don't know what is mu s and mu b. Then the fit gives you something like mu s equal to 8.7 and sigma s equal to 5.5. The error on the sigma s. Okay, so that was what I mean. It means using the extended maximum likelihood. So most of the time when you do this kind of fitting, you basically try to do the extended maximum likelihood fit. So we can do some similar kind of, I mean, this kind of fits using RuFit in your exercise. Is it understood?
Sir, in the previous slide, you wrote f of x is equal to mu s by mu s plus mu b. I don't understand the normalization factor, like why the means are here.
So yeah, what you did not understand?
Sir, this normalization part, I mean mu s by mu s plus mu b, why does this factor comes?
Because the PDF has to be normalized, right? If you don't do that, you will not get its f of x dx to be 1.
So, sir, I mean, we could have used number of events also. So, like, why mean?
Which you mean by number of events?
I mean, sir,
ns, you mean ns by ns plus nb?
Yes, sir. Yes, sir. Yes.
Yeah, but the point is that here why the ns is not, I mean, n is total number of events that we are observed, right?
Yes.
And we don't know what is NS and NB exactly. Okay, but we assume that and NS and NB is basically Poisson distributed with the true value to be mu S and mu B. So what you observed from is NS and NB, but which you don't know, you observe just simply NS plus NB, okay, from data, and the true values are mu S and mu B.
Okay,
To
sir.
mean, okay, and
Yes.
this N is Poisson distributed. So you can simply do NS. Then in that case, you will assume that NS is your true mean, and it's just how you write it. The point is that mu is the true mean of for NS, and mu B is the true mean for NB, and NS and NB is simply drawn from the Poisson distribution for mu and mu S and mu B. So when you do some experiment, you will get some fluctuations, right? You will not.
Yes, sir.
If the true value is mu, you will get something n, which is mu S plus something, which is distributed according to the Poisson distributed. That's all. So what we want to get is what is the true value that we can. So that's why we use this as also we did not keep this as fixed, but if you make this as fixed, you will get only fx and fp. Then you are fixing the number of events. If you don't treat as parameter, then you are fixing the number of events.
Yes.
Sir, can you go to the next slide? So here we want to estimate the mu S. So, so after performing the fit, the value of the mu S we get is 8.7, and the spread, the second parameter we get is 5.5 for the
Yeah.
sigma.
Yes.
But okay, so this is in I mean what space, because here we can see the pattern distribution function, or maybe the sorry, the probability distribution function f of x as a x. So the signal is centered around 1. So the mean is at 1, but the parameter, the fit parameter is we are getting is around
The
8.
mean of x is at 1, which is the distribution.
The fit parameter may have different value.
Yes. So I mean the fit parameter here, the x is the variable that is centered around 1. Okay. I mean, like if you say mass or something, or some other parameter, some other variable which is centered around 1. Okay, but the parameter here is the mean, which is nu times your theta, whatever. So it's in this case mu is simply nu times the theta.
Okay.
Okay, so in this case the parameter is mu, and you are basically getting the normalization component for each of these two components in this case. But you can have, of course, more parameter or something, but this is simply you are getting, assuming that you have the Gaussian PDF and sorry, the PDF for the signal and PDF for the background. Then you are fitting together to get, given my number of events, how many of them are signal and how many of them are background.
Yes. Okay.
Did you get my point?
Yes.
Yeah. Okay. Now this is so far what we discussed. It's on wind, and we basically plot it in terms of beans, but when you read the fit, you actually use individual events. Okay. To define the likelihood. But you can also do the bin data, fit to the bin data, particularly useful when the data set is very large. And then, doing it on bin for such a large data sample, it may be, time consuming, slow, and so on. So it's possible that, I mean, it is easier to do, make histograms and then do a fit to the bin data. Okay. So in this case, so suppose that we have some n number of events, and we made a histogram of n bins. So individual numbers in each bin corresponds to n1 to nn, depending on the number of bins, and sum over this number of bins is n total. Okay. Now the number of, so this is again, you can treat them ni's are Poisson distributed, okay, with some mean values mu. Then the mu or of the number of entries can be written as mu I, which is function of the parameter, as n total times the integration of this PDF within the bin range. Okay.
Sir,
Now,
can I have a confusion here. So here, if I understand correctly, so this expectation values mu is actually the probability that a particular bin I will receive a entry n1. Is it like that?
this mu I is it's not just the probability. Probability is this times the integration, the component which is integration of x beta d theta within that bin range. That's the probability times the total number of events gives you the expected number of events in that bin.
Yes, exactly. Yes,
This is the expected number of events in the bin I.
bin I. Okay.
Now, now you can consider this histogram as a single measurement, okay, of n-dimensional vector. Then you can write a joint PDF that what is the PDF that I will get new one events in bin 1, new 2 events in bin 2, new 3 events in bin 3, and so on. Okay, so that will be my multinomial distribution, right? Given total number of events I observed n total, what is my probability? Assuming that I know what is the PDF, okay, that what is the probability that we'll get new one events in bin 1 and new 2 events in bin 2, and so on. So that's the joint probability given by a multinomial distribution. So that's what it says, right? Whereas for individual bins, the probability is mu I over n total. And then you can write the log likelihood function, which is given by this plus some constant. Okay. So this is big. Now you can see that this will be ni times log mu I. Okay. Now, given this log likelihood function, you can perform the fit to the histogram and get the parameter theta and mu. Okay. Now here is the example for sample with a 50 measured particle decay. This is the same example that we did earlier with on-bin fit. Correctly. So which one was that? Yeah, this one. We generated 50 decay times. We did the on-bin likelihood fit to these 50 events. Okay. Now we do the same thing here, but with binning. So you do the binning first, and then draw the histogram, and then fit to the bin, the histogram itself. Okay, using this log likelihood function. So in this case, the bin width here are delta t equal to 0.5, and there are say like 20 bins, 10 bins from 0 to 5, which has decay times. Now, if you do these fits, assuming this function is exponential, then you will get tau value of the estimated value of the lifetime is 1.067. This is pretty close to what we got from the on-bin result. So this was on-bin result was how much? 0.1. Yes. Yeah, 1.062 that, and this you get very pretty close to that. Okay, and what was the sigma here? Yeah, the sigma, it's this. Yeah, sigma was, I think, around 0.1, 1.059. Is it the correct one? No, 0.15. Actually, sigma is 0.15. So if you do the same thing here, and what is the result, you can see. So slightly larger than the unbent result. Okay.
Sir, now here at this point, I have question. So I mean, the question here one can ask is, how confident I am about my tau and sigma. Let's say if I would have been a much more finer, I mean, I would have much more finer bins. So will my result, the fit result will be bin dependent, and up to what extent? It will be.
Yeah.
Because when you deal with the real problem, then I mean it becomes a very big source of systematics in your analysis.
Yes. So the point is that here, if you do very fine binning, then the uncertainty on individual bin events becomes very large. Okay, so that contributes to your the measurement error. Okay, so you need to have some kind of balance that the errors on individual bins and the uncertainty on individual bins, the fluctuations in individual bins is smaller. So that's why this method I mean, this is useful to do this bin one when you have a large data set. So if you have small data sample, it's possible that you can do on-bin likelihood fit. Like you
So,
just
is there any particular scheme to do the bean optimization? Like, let's say we do not have that much of data that we can do some kind of uniform binning, or we can do the way you just showed. But let's say we have some number of events, and we want to do in the binning schemes, like we need to do in the bin fit. But is there any bin optimization scheme, like let's say
I
there
think
is.
it will be bin optimization. I don't know, but it would be better to check also the what I mean, it's a check the chi-square values in this case. Okay, and the goodness of it, to see if your goodness of fit value is good. Okay, so otherwise, or also you can check the error, estimated error that you get, and try to optimize. If you say improve the binning, whether you will get smaller error.
Because sir,
I don't know if you have a
why I'm saying,
particular way
because
to do that.
let's say we have some 3 year of exposure. Let's say we are doing certain experiment, and in the 3 year of exposure we have collected some of events, and we have done some kind of analysis using some uniform bin or some binning scheme. But then when we integrate our let's say the detector continues to receive some events, and for then after 10 year, if one wants to do the calculation in the same way, then the events have already increased, and for that we need to do further binning.
Yeah, you can do smaller binning.
Yes.
Yeah.
So for
As
that,
the statistics improves, you can do smaller and smaller binning. Then it will become more like a continuous distribution.
continuous distribution. But let's say In between that, I'm particularly talking about some neutrino events. Let's say there is some supernova, and for particular beam energy, some energy range, we are getting some handful of number. So for that region only, if we take a particular binning scheme, and other that if we exclude it, then the result will change. But when let's say we take from this last 3 year data, and then the next 10 year of data, then those effects are getting diluted. So my question was like, is there like the way we are doing the fitting under those things, so do we have any proper scheme to optimize the beam, like the scheme?
This I'm not sure. Maybe you can discuss this during the school when we have more experts.
Okay.
This I'm not sure if there is a way to optimize the bin. One way to do people do the binning is to keep the relative error, I mean similar for each bin. For example, one of the way that you try to do in the search that you have say less than 10% error in each bin, kind of thing, so that you make a variable binnings in that way.
Yes, okay.
That kind of thing it's done, but I don't know if there is some particular scheme that can optimize the bin.
I think yes, sir, you are correct. There is, I mean, for my knowledge also, I mean, I have asked this question to, I mean, several people, but what I get the best answer is that, I mean, you have to look it by your eyes and your data and what you are doing and what your histograms are filled with, and accordingly you have to do
Yeah.
your binning.
Yes, I mean it's like more like an experience than really some the formal method. And yeah, so because if you make very small binning with a less number of data, you get much more statistical uncertainty and fluctuations, bin by bin fluctuations. So you can have some bin very large, some bin very small. So that doesn't help, right? So try to make it a way that the bins are in such a way that for each bin the errors are more or less similar. Okay.
So what do you mean by errors are more or less similar?
And the uncertainty is in each bin, so which is square root of n kind of thing for each bin.
So square root of n, the number of events in that bin.
You can do that way. I mean, one of the ways that you can make the number of events. Sometimes if it is a weighted, then you have to take weighted things and so on. Yeah, but if you see this kind of distribution, say like exponential, you would not expect that the number of events would be same.
Yes, sir.
Yeah, so it basically depends on what you want.
Okay, sir.
So yeah, I mean the point is that the statistical errors in the bean should not be very large, and the bean to bean fluctuation should not be also large. I mean the point is that you can have, if you make very small bean with less no data, you can have one bean very high and the next bean very low. That's what I mean. So it doesn't look like continuous, right? So I mean, you can do this kind of exercise with some pseudo data in Europe. It's just generate some data with a different number of events and play with maybe uh, the bin size and see what you get as the field value and the error as well as the chi-square value. Now Yeah, we can probably ask the same question when we have more people here and see what experience people have. Okay, and now let's go to the next thing. So in this case, we did not treat the n total as a Poisson variable in this case. But now, if we treat again that the n total itself is a Poisson variable, that with the actual mean is new total, okay, then you will again have to multiply this additional Poisson distribution for the n total, okay, given mu total is the expected mean, okay. So from that you will get the joint PDF is this times the multinomial distribution, okay. So here we only use the multinomial distribution. Now we multiply to this an additional Poisson distribution. Now if you do that, so now you can rearrange these terms, and you will see that this is simply a product of the Poisson probabilities for the individual beans, okay. And yeah, and here the expected number of entries in each bin. Now you can see that earlier we had nu I of theta, it's n total times, since n total was constant and we are not treating this as a Poisson variable. Now it is, since n total is Poisson variable, now we get nu I as nu total times the probability to be in that bin, okay, which is given by this f of x theta d theta dx integrated over the bin edges. Okay. So now this becomes like equivalent to treating the number of entries in each bin as some kind of independent Poisson variable. Now if you do, now you can calculate the log likelihood, then that becomes the total mean total plus the sum of the ni times log of nu I, which is function of theta and the total nu. Okay, so this is basically same as the extended log likelihood function, but with bin data instead of the on-bin data. Okay. Yeah, so I do not have this any example here, but you can do something later on this. So my idea was that I just try to give you the concept so that you can go through it, and when we have some exercises in the school, you will be able to understand what comes from there.
Sir, actually, can I make one comment here?
Yeah.
Actually, this is the perfect example of what in a real histogram, I mean, it happens because I was trying to find out the reason behind it, but actually it is assumed that when you have a histogram and you have a n number of bins, so the probability that the particular bin will have an entry n1 is Poisson distributed, and you have to, follow this, Poissonian statistics. But
Yeah.
but why? I don't know. Maybe if you know, you can, throw some light on that. Why a histogram, each bin will expect the probability of its bin distributed with the Poissonian. I don't know.
Yeah, the Poisson distribution we discussed yesterday, right? So Poisson distribution comes when you have um, from the you have n, it's not very large. The number of events is not very large. So in that case, so you get the distribution to be Poisson, right?
Yes, yes.
So that's why we are not treating this as a Gaussian, but Poisson, because that condition. Let me find what is the condition for Poisson. Yeah. So the Poisson is basically when you have n becomes large, and then the p, the probability becomes small. So then np is basically, it remains some finite values. Then in that kind of cases you get the Poisson distribution instead of binomial.
Okay. Yeah.
Okay, so
I think maybe for moving from more ideal case to realistic case, because
yeah,
experiments we have, even though we have large number of events, but they are ideally not infinite. In
yeah,
case,
so that's right. So only when it becomes from Poisson you can go to Gaussian in some limit, right? When the number becomes very large, or something. It's the exact condition. No. What is the exact condition going from? No, well, you can discuss later these things. Not sure if anyone knows this. What is the exact limit from going to Poisson? No, okay, we can come back to this maybe during the school. Okay, let's continue. Okay, I'll come back to this goodness of fit test after I discuss the chi-square, because that will be a bit easier than this. Okay, let me first go to chi-square, least square method, and then, because we'll be using again the chi-square test statistics here, even in case of this maximum likelihood. So let's come from the other direction. Yeah, okay. Let me now let's discuss first the least square method. Okay. Now, assume that you have, say, measured values y, okay, which is Gaussian, which is a Gaussian random variable, and centered around some true value lambda h. So you have n measurements of such uh, Gaussian random variable yi, okay, which is some function of xi. For example, you are measuring, say, some temperature as a function of time or something like this. Okay, and these yi's are actually drawn from a Gaussian distribution where the mean value is, the true value is some lambda h. Okay, then you assume that this yi's have different unknown means lambda is, and the variance of of this Gaussian distributions are known, which are sigma I square. Okay, so if these are known, then you can regard, suppose you have n such measurements yi, then you can think at it as a single measurement of n-dimensional random vector. Okay, that the probability to get all these yi, given that we have the true values are lambda I, okay, lambda 1 to lambda n, and we know what is the variance sigma, will be simply the product of these probabilities. Okay, so we can write the PDF for obtaining this yi, given the true values lambda 1s are the product of n such Gaussian distributions. Okay, now imagine that this lambda is a function of some parameter theta, okay, which is theta 1 to theta n, some n parameters which are unknown. Our aim is to estimate the parameters theta. Okay, now we can try to do the same way as we did the likelihood method. So this is the joint PDF, so we can write now this joint PDF as our likelihood function, which depends on the theta, and maximize this with respect to theta. Okay, so then we can write this log likelihood function, which is basically the sum of this, given that this is the PDFs are Gaussian, then this will become simply the sum of this quadratic terms. Okay, and then when you maximize this log likelihood, and you can now see that this is negative, right? So maximizing this L would be equivalent to having minimizing simply this sum of these quadratic terms. Okay, so now you can define this the sum of these quadratic terms is basically a chi-square. Okay, so that's, you can see that this chi-square is kind of a special case of maximum likelihood method in the case where the PDF is Gaussian. Okay, you can see this in this picture as that this if you have, say, this kind of points where these yi's are drawn from a Gaussian PDF with mean lambda i's, okay, and the sigma is of each of these error is corresponds to the sigma is, they are known, then the lambda, the function, okay, which depends on the parameter theta given the xi is given by this, function, okay, and then you feed this function to these points using this by minimizing this chi-square. Okay, so this is the basis for least square. So you probably, whenever you try to learn group from the beginning, you try to basically do some function fit, okay, to some points, so to some graphs or histograms, and you use this chi-square minimizers in that case. So this is the method of least square, and even if yi's are not Gaussian, as long as they are independent, this method is still being used, this chi-square method, and the estimators which are obtained from this chi-square method are called LS estimators, like we had earlier, ML estimators. And the resulting minimum chi-square, okay, when in in certain cases or certain circumstances, follows the chi-square distribution. We discussed about chi-square distribution. Do you remember, or I should go back to that? Okay, let me maybe go back to that because I'll talk about it again later. Yeah, you can see this. So this is the PDF for the chi-square distribution that we had seen earlier. So the Z here is what we defined there, the sum of these quadratic terms, okay, and giving the number of degrees of freedom n, the f of z has this expression, and you can see for this n equal to 5, you can see the distributions of this chi-square distribution. Now, if you compute the mean of this z for this distribution, it will be same as the number of degrees of freedom, and the variance of z is twice the number of degrees of freedom. Okay, and since this chi-square that we defined there, here we write this as z is distributed according to this distribution f of z, which we call the chi-square distribution. So we use that quantity there, usually called a chi-square. Okay. Did you get the point? Okay. Now can go back. So okay. So if that what we discussed here, that all these parameters were uh, independent. Okay. Now it is possible that I mean the points are independent. Now it is possible that the yi's are not actually independent, but they are actually drawn from a n-dimensional Gaussian PDF, joint PDF, okay, with some known covariance matrix. Then in that case, you can write again the log likelihood function as log of L, this parameter theta, as now the sum of y minus lambda times this inverse of the variance times, I think, probably. Yeah, and then this y minus lambda. Okay. Again, this. Yeah, okay. Then you can define the chi-square as simply removing this minus half factor, so that you can minimize the chi-square to get the corresponding theta estimate for the theta. Okay. Now, if v is the diagonal, then you can see that the off-diagonal term will become 0, and then this expression will be basically reduced to this expression here. Okay, with diagonal terms being sigma square. Okay. Now, giving this, definition of the chi-square, now let's see how we can perform a fit, okay, and what is typically, I mean, we can consider for the functional form of the lambda, okay. So when lambda it's a linear function of theta, that means you can write uh, lambda to be something like yeah, okay, like lambda. should be L. Sorry, I made some mistake here. This should not be L, this should be lambda. Okay, I can make this correction in the slide. So this should be lambda of x theta to be sum over some aj x theta j. So that means you can say that so aj x not necessarily to be linear in a function of x, but it is simply linearly independent. That means you cannot write one a j to be some linear sum of other ai's. So they are linearly independent, but it doesn't necessarily have to be say linear in x. Okay. And then yeah, so then you can write this lambda as a linear combination of these thetas. So in this case, this estimators and the variances can be found analytically. Okay. Also, the estimators have zero bias and minimum variance. Okay. So if you now write this again, I made mistake. This should be lambda. So if you write at xi, this will be lambda times xi theta to be sum over aj theta j, or if you write aj of xi is some kind of matrix aij, so you will get lambda of xi theta to be sum over aij theta j. Okay. Now in matrix notation, the chi-square, okay, which is written as y minus lambda transpose v inverse y minus lambda, now can be written in place of lambda. You can write a times theta. Okay, so you will get this this chi-square, and here y minus a theta will basically kind of a column matrix. Now, if you minimize this chi-square with respect to theta I, then you will get delta chi-square as minus 2 times this factor, and minimizing means makes it a 0, would give you that theta at, or the estimate for theta to be A transpose V inverse A inverse times A transpose V inverse Y. Y means the measured values itself. Okay, that means you can write this as some matrix B times Y. So that means theta hat is simply a linear functions of the original measurements Y. And similarly, you can use the error propagation method to find the corresponding covariance matrix Uij. Okay, and the expression for U will be simply B transpose, which will be nothing but this A transpose B inverse A of inverse, or equivalently, if you take the inverse of the covariance matrix, then it will become half of del square chi-square over del theta at del theta j at theta equal to theta hat. Now you can see that this is basically coinciding with what we got from the ML estimate, for the ML estimator in the using the RCF bound. When yi are Gaussian distributed, this coincides with the same expression as we get from the RCF bound. Okay. Now you can we can also obtain the variances for the LS LS estimators. Now you do similarly. We did expand this chi-square like we did expansion of the log likelihood around the estimate itself. So here you can do the same thing. You expand the chi-square around the LS estimate theta hat. Then the first term, which is first derivative term, will become 0 at theta equal to theta hat. So what will remain is the second derivative term, right? Now, if you combine this expression with the variance here, okay, so you can write that theta equal to when you vary the theta by its one standard deviation sigma I, then this you can see that the chi-square changes from its maximum value by 1. Okay, so if you change theta is by its variance sigma I, and sorry, square root of the variance sigma I, you will get chi-square theta to be chi-square theta chi-square at theta hat, that is chi-square maximum, sorry, chi-square minimum plus 1. Okay. So this is equivalent to the contour that we saw earlier. So in this case, you will get again, if you have more than one parameters, say 2 parameters, you will get a contour, elliptic contour, okay, with constant likelihood or constant value of the chi-square, which is differs from its minimum value by 1. Okay. Now, if lambda is not linear in theta, then the contour will not in general be elliptical. Okay. So you can have, of course, lambda not exactly a linear function of linear combination of theta, but then in that case you can still get this contour, but this will not be elliptical. So the tangents that we saw that corresponds to one standard deviations will not exactly correspond to one standard deviation, but you can still define a region in parameter space which can be interpreted as confidence region. Okay, so this confidence interval will be taught later during the school. Okay, basically when you don't treat this uncertainty as Gaussian, in that case this you cannot basically treat error as one standard deviation and you will get the confidence region. Okay, now this is one example from this reference. So you can see that this is a least 12 fit to a polynomial. Now this 5 point, this is basically the 5 points are drawn or it's a measured from some experiment or just drawn using some parameter using some parameter, and then you draw the individual points assuming the mean value lambda and then Gaussian distribution around lambda. Okay. Then you try to fit these 5 points using different polynomials. Okay. Now in this case, the polynomial a of x, ai of aj of x is simply x to the power j. That means you can have, say, if it is a zeroth order polynomial, you just simply as a constant. If a first order polynomial, you have ax plus b kind of thing, or second order you will have x square plus bx plus c, like that. Okay. So the number of parameters for polynomial is simply m plus 1 parameters. Okay, m coefficients of x and then one constant. Now you can see the fit values. Now the interesting point is you can see that when you have try to fit the zeroth order or constant to these points, you get very high values of the chi-square. That means it doesn't fit very well. Okay. Now if you try to fit first order, you get chi-square to be something like around 4. So this looks a bit reasonable. Now the fourth order, which is 5 parameters, and now you have only 5 points. It fits exactly to these points. Okay. So which you can, like, the chi-square becomes simply 0. So there will be no, and since it goes through exactly through all these points, because it has high number of parameters, it's same or equal to or more than the number of points, then you will get the power passes through the each individual points. Okay, so you can think that as kind of an overfitting issue. Okay. Okay. Now, from this fit, you can see what is the estimate, what is the uncertainty on the individual parameters. So the left plot basically shows you the 1 sigma or 1 standard deviation for when you try to fit a constant or zeroth order polynomial, okay, where the chi-square was very high. So here you see that when you change the value of this parameter, the point where it changes or becomes 1 higher than the chi-square mean, that corresponds to the 1 sigma or 1 standard deviation. So here you can see that the chi-square mean is at 45.5, and then when as you change the theta 0 constant in both sides of this optimal value, then you can see that in both cases the chi-square increases, and when it touches chi-square mean plus 1, that corresponds to the 1 standard deviations. Okay, and that gives you the uncertainty on theta 0. But here you can see that from this uncertainty on theta 0, you cannot really say that this hypothesis, so the function that you are fitting, is actually correct. Okay, this basically what this error means is that if you have n such experiments, large number of such experiments, each time you get say same 5 points, okay, and then every time you feed the same function, assuming that this function is correct, the distributions of the parameter value that you will get from n such experiments will have some distributions, and the width of that distribution will give you this error. Okay, that's what it actually means. Okay, but that doesn't actually tell you that the hypothesis that you are fitting is the correct hypothesis. Okay. Similarly, when we do this first order fit to the first order polynomial, then in that case you have two parameters. So you will get the 1 sigma contour or 1 standard deviation contour. So it's elliptical, okay, which corresponds to, like we discussed earlier, in case of maximum likelihood fit, where the maximum likelihood fit value of the value of the log L changes by it reduces from its maximum value by half. In this case, the chi-square increases from its mean by 1. So this contour represents that. So all these points were corresponding to these two parameters, where the chi-square value you get is chi-square mean plus 1. So that gives you the 1 standard deviation contour. And the tangents to this contour gives the 1 standard deviation value for this visual estimators, or which we call it the error on theta 0 and theta 1. Okay. Now another thing that you can see in this case is that this theta 0 and theta 1 are actually highly correlated, because you can see the angle of this ellipse is very high. So that you can also get from here, okay, by computing the covariance values using the this expression here, Uij from its second derivative. Okay. So when such kind of correlation is observed, it is important that when you provide the fit results, not only you provide the error on the individual parameters, you also provide their covariance or the correlation coefficient in the fit results. Okay. Now, what we discussed so far is the least square fit to individual points, right? Now we can discuss about when we want to fit perform this least square fit to some bin data, okay, like we did for the maximum likelihood. Now you can consider, say, again, n observations of x which are filled into a histogram with n bins, okay, and then here the yi's are basically treated as the number of entries in each bin, okay, and f of x theta is your hypothesized PDF, okay, which we expect that will fit to this histograms. Then the number of entries in bin I, f of x theta, the number of entries in this bin I lambda I will be the expectation value of the yi's, okay. So where you can write lambda I theta to be n times the probability for the events to be in bin I. Now you can as you see that the lambda is now proportional to the PDF of x, okay. Earlier we treated that lambda are any functions of x, not necessarily to be the PDF of x. Now in case of the bin data, what happens that lambda becomes proportional to the PDF of x or depends on the PDF of x. Now you can write again the chi-square function for this kind of bin data. So it will be basically like yi minus lambda I over sigma I square, okay, and sigma is the variance of the number of entries in bin I, okay. So when we treat the number of entries in bin I to be Poisson distributed, okay, in that case simply the variance becomes the mean of this variance is same as the mean. So you can write that since lambda is at the expected number of events in bin I, assuming that that's the true mean, so then you can write the variance as the lambda I. Okay, now our chi-square becomes like yi minus lambda I square divided by lambda I, or in other words, you can rewrite lambda I as in terms of the probabilities. So n times pi. Okay, so that is one way of defining the chi-square. Now you have another alternative method where instead of using the true mean or the expected mean lambda I as variance, you can simply use the observed number of entries in the bin yi to be in place of the variance, in place of the variance. So then in the denominator, instead of lambda I, you can write yi. Okay, so this is called the modified least square method. Okay. So the advantage of using this modified least square method is that this is computationally easier, but there are disadvantages like the errors may be poorly estimated, or even the chi-square may be sometimes not well defined if the bins contains very few or no entries. Okay. Now, before going to the goodness of it, I want to discuss a little bit about the least square fit, what is the advantage and disadvantage of least square fit, and the maximum likelihood fit, what you usually to prefer. Okay. So you have to keep in mind that when you do this bin likelihood fit, particularly the bin likelihood the fit to the histogram. So when you do this fit, sometimes instead of n total here in this expression of lambda I, what you do is you use a normalization parameter mu, okay, instead of the total entries n. So here you put a mu here, which becomes a normalization parameter. You assume that n is not the exact number. You expect some y. So in this case, however, that this can lead to incorrect estimate of number of entries. So for least square method, you can have you expect that the estimated value of this mu from the least square method would be n, okay, after the fit. But sometimes you may not get this. You will get n plus chi-square by 2. And similarly, for modified least square method, you will get if you minimize this chi-square, you will get that the estimate for mu would be n minus chi-square. Okay. Now you know that if you have n bins, from each bin you get a contribution of 1 to chi-square, right? So if you have large 20 bins, you'll get, say, chi-square will be 20 minus the number of parameters and so on. Okay. So if you have large number of bins, okay, so you'll get that this value chi-square by 2 or chi-square will be some large number. In that case, you may actually get the estimated value of nu, not exactly 1. It will deviate a lot from not exactly n, but it will deviate by large numbers from n. Okay. But when you do the same thing in the ML method that we discussed earlier, where we treated the number of events in the bin as a Poisson variable, nu. In that case, we had a PDF which was product of the Poisson probabilities for each bin. In that case also, we treated nu as an adjustable parameter, right? But in that case, when you get the estimate of the nu, you will correctly get the estimate that to be n. Okay, so that's one advantage of being using ML fit method for the bin data instead of using least square method. So when you try to fit the histogram, this is advantageous to use maximum likelihood fit instead of the least square fit. Yeah, this gives an example from this book, which shows basically what we discussed here, that it generated, say, a data set with 400 events, okay, using a PDF, which is similar to what we discussed earlier, like a Gaussian plus an exponential, okay, with parameters theta and 1 minus theta, like we had mu s and mu b. Okay, so these events are generated with some values of these parameters theta, mu, chi, and sigma, where mu and chi and sigma are supposed to be known, and we want to fit this to get theta and nu. Okay, so when you perform the fit, so here there are 4 different fits that have been performed. One is this least square method, where you treat this nu as an adjustable parameter. In that case, you can see that for 400 events, you get something like 408 events. Okay. Similarly, so it is overestimating because we have n plus chi-square by 2. Similarly, when you have a modified least square method, you get something like 382. Okay, so this is lower than the actual number of events. And when you do a least square method but you do not treat nu as a adjustable parameter, but keep it fixed as n. then you get the chi-square small around same value, but mu is basically the fixed. But when you but in case of maximum likelihood, where you treat mu as adjustable parameter, in that case it gives exactly the same number of for the normalization, that is 400. Okay. Yeah, so that was it shows basically why ML method using ML method it's advantages compared to the least square method when you do fit to the bin data. And there is of course some other things in that case which I'm not discussing, like convergence and so on. Okay, now let me come to testing the goodness of it. So we shall discuss that if y i's are the these variables or measurements are Gaussian, then the resulting estimator coincides with the ML estimator. Estimator for the least square coincides with the ML estimator. Now, this quantity yi minus lambda by sigma, it basically gives you a measure of the deviation between yi and the true function lambda, right? So we can use this chi-square as a measure of total agreement between observed data and hypothesis. Okay. Now, if these conditions, these three conditions satisfies, means if yi's are independent Gaussian random variables with known variances, or this is an n-dimensional Gaussian with known covariance matrix. Okay, and the hypothesis lambda is linear in theta. Okay, and the functional form of the hypothesis is correct, then the chi-square mean, the minimum value of the chi-square is distributed according to the chi-square distribution with n minus m degrees of freedom. Okay. Now, from the chi-square distribution, we discussed earlier that the expectation value of z, which is distributed according to the chi-square distribution, is equal to the number of degrees of freedom. So if we now take that the chi-square per number of degrees of freedom can be used as a measure of the goodness of fit. Now, from the fit, if we get that the chi-square for number of degrees of freedom is similar to 1, this we can say that the fit is good. Now, on the other hand, if chi-square for number of degrees of freedom is much less than 1, then we can say that this fit is too good, but this can come because we have either overestimated the errors or the errors are correlated. Okay, so we need to check that these errors are not overestimated. Okay. On the other hand, if chi-square for number of degrees of freedom is much larger than 1, then you have to decide whether this hypothesis is correct or can be rejected based on the p-value of this chi-square value corresponding to this chi-square value. That means what is the p-value? The p-value here is the probability that you will get the chi-square equal to or more than the chi-square that has been observed. Okay, that means if you take the chi-square distribution and integrate over the values of the obtained chi-square up to infinity, that gives you the p-value. Okay, that means if I now go back and just show it here. Yeah, so suppose we got for this number of 5 degrees of freedom, we got chi-square value to be 10 from some fit. Then we will get the p-value as the area under the curve from 10 to infinity. So that gives us the p-value, and depending on the p-value, okay, so we'll say whether we can still think that this hypothesis is correct or not, okay, for fitting this particular set of data. Yeah, okay. Now this is regarding the goodness of fit for the least square method. Now I can go back and discuss about the goodness of fit for the this for the maximum likelihood method. Now for the maximum likelihood method, the principle of maximum likelihood usually doesn't directly suggest a method of testing the goodness of fit. The one possibility is to use the value of the likelihood function at its maximum, Lmax, as a goodness of fit statistic. However, we don't know what is or how the maximum value of the likelihood is distributed. Okay, because unlike the chi-square function, where given the number of degrees of freedom, what is the distribution of the chi-square. Okay? But in this case, you don't know what is the distribution of the likelihood. Okay, so to get this distribution, in order to know that the observed likelihood value is good, you can do some Monte Carlo studies. So what you do is that you can get a distribution of the PDF of the maximum value of the likelihood using the Monte Carlo method. So what you get is you get first the maximum likelihood estimates from the real data, and then use that estimates to produce or generate large number of Monte Carlo distributions from each set of Monte Carlo data to do the maximum likelihood fit and get what is the value of the maximum likelihood for that particular set of data. And then from n such experiments, you get a distribution of the maximum likelihood. Okay, now suppose your distribution is the total distribution here for this log Lmax, and from the real data you got the actual log max is in this region, the straight line in between. Then the p-value would be the area under the curve below this Lmax value. Okay, and from this p-value you can say that whether your fit is good or not. Okay, so that is one way of testing the goodness of fit for the maximum likelihood method. Now the other method is can construct an histogram n with n bins from the total number of measured values. Okay, where nu hat are our estimates for the mean values from the ML fit. Okay, where nu hat is basically n total times the probability of the events to be in that bin. Now you can construct a goodness of fit statistic using the data n and estimates nu, and then consider a likelihood ratio. Okay, so likelihood ratio is the lambda is the ratio of the likelihood for getting n given expected as nu to be over the likelihood of getting n given expected to be n. Okay, n events. Now this is basically, this likelihood is nothing but the joint PDF of getting the n events given we expect to have new events. Okay, now if n total is fixed, then f joint is basically given by multinomial PDF. Okay, and if we treat n total to be a Poisson variable, then F joint will be simply a product of the Poisson probabilities. Now, given this, we can now define, in case of the multinomial distributed data, we can get this test statistics, goodness of fit test statistics, lambda, to be simply product of the nu i's by ni's to the power ni. Okay, because the other factors will cancel out. Now, if the hypothesis is correct, then in the large sample limit, the statistic chi-square, which you can define as chi-square to be minus 2 log lambda, will give you this value twice times this sum, and this chi-square statistic will be distributed according to the chi-square distribution that we discussed in the least square method for n minus m minus 1 degree. Okay, and where m is the number of parameters here. Okay, estimated from the top. So from this chi-square statistic, given the observed value of this chi-square m, you can now say, and we know what is the number of degrees of freedom, you can now say that whether our maximum likelihood fit was good or not. Okay. Similarly, in the other case, when you treat n total to be a Poisson variable, then the Poisson distributed, in that case, you can write the lambda p as this exponential factor times what we got from the multinomial distribution. And then you can again similarly define the chi-square for this case, twice log of lambda minus twice log of lambda. And here in this case, this chi-square will also be distributed according to the chi-square distribution, but for n minus m degrees of freedom. Okay, so 1 degree and higher, 1 degree of freedom higher, more. Okay, so again from this you can see that whether your chi-square statistics is whether your p-value is good or not, given the chi-square distribution for this number of degrees of freedom. Now you can see that since the denominator in this likelihood ratio does not depend on the parameters, right? Because nu only depends on the parameter theta. So L, n given n doesn't depend on the parameters. That's why the parameters theta that will maximize the likelihood L of n given nu will also maximize lambda, right? Therefore, instead of the likelihood, you can use this ratio of the likelihood for constructing both ML estimator as well as the goodness of fit statistics. So you can do the both with the likelihood ratio instead of simply the likelihood. That's also one advantage of using this likelihood ratio. Okay, so another approach is exactly doing just defining the Pearson chi-square statistics. Okay, just simply from the number of events in the bin up to the fit. So ni is the number of events observed, and nu I is the estimated number after the fit. Okay, and then you just simply define the chi-square statistics, test statistic. And when n total is treated as Poisson variable, you can, instead of nu I, you can define use that pi times n total. Okay, and in both cases, again, this will be both this chi-square will be distributed according to chi-square distribution, and from the observed chi-square value, you can know whether the fit is good or not. Okay, yeah, that's all from my side. If you have some questions, we can discuss. Okay, I see that there are no questions. Okay, if not, then I think we can close here and this videos